We humans have always gazed at the stars, filled with wonder. Those distant suns sparked our curiosity. When did they ignite? How old is our universe? These questions have echoed through generations. Today, we have a powerful tool to unlock these cosmic secrets: nucleocosmochronology. This field of study allows us to estimate the age of stars and even the universe itself. It's a remarkable blend of nuclear physics and astronomy. Imagine deciphering the universe's history written in the hearts of stars. By studying the elements within stars, we can trace their lifespans and understand the grand timeline of the cosmos. It's like finding an ancient artifact and using it to piece together the story of a lost civilization. Only, in this case, the artifacts are stars, and the civilization is the universe itself. Our journey begins with understanding how stars create elements, the very building blocks of matter. From the carbon in our cells to the gold in our jewelry, these elements were all forged in the fiery hearts of stars. Nucleocosmochronology hinges on a fundamental process: radioactive decay. Certain atomic nuclei are unstable. Over time they break down, transforming into more stable forms. This process is like a ticking clock, marking the passage of time. Think of it like an hourglass. The sand in the top represents the original unstable element. As the sand falls, it transforms into a different element, represented by the sand collecting at the bottom. The rate at which the sand falls is constant, just like the rate of radioactive decay. Each radioactive element has a characteristic half-life. This is the time it takes for half of the original atoms to decay. By comparing the abundance of the original element to its decay product, we can determine how long the decay process has been going on. This gives us a measure of the object's age. In the case of stars, we look at the decay of elements like thorium and uranium. These elements were formed in the early universe and incorporated into stars as they were born. Measuring their decay products in stellar spectra allows us to estimate the ages of individual stars. Stars are cosmic furnaces, churning hydrogen and helium into heavier elements through a process called stellar nucleosynthesis. This process is the lifeblood of nucleocosmochronology, providing the crucial ingredients for our cosmic clock. Imagine the intense heat and pressure deep within a star. Under these extreme conditions, atomic nuclei collide and fuse. Hydrogen atoms combine to form helium, releasing tremendous energy. This is the same process that powers our sun. As a star ages and exhausts its hydrogen fuel, it begins to fuse helium into even heavier elements like carbon, oxygen, and nitrogen. The heavier the element, the higher the temperature and pressure required for its creation. The most massive stars can even create elements as heavy as iron through fusion. When these stars eventually explode as supernovae, they release these elements, along with even heavier ones created during the explosion, into space. These elements eventually become incorporated into new stars and planets. Section 4, Isotopic Ratios, the universe's timekeepers. Now let's talk about isotopes. Isotopes are like siblings of an element. They have the same number of protons but different numbers of neutrons. This means they behave chemically the same but have slightly different masses. For example, carbon-12 and carbon-14 are both isotopes of carbon. Carbon-12 is stable, while carbon-14 is radioactive. By measuring the ratio of these isotopes in a sample, we can determine its age. In nucleocosmochronology, we use the ratios of certain radioactive isotopes and their decay products. These ratios serve as a cosmic clock, revealing the time elapsed since the elements were created. By analyzing these ratios in stars, meteorites, and even on Earth, we can piece together a timeline of events in the early universe. These ratios provide valuable clues about the age and evolution of our cosmos. Section 5. Unlocking Cosmic History. Nucleocosmochronology has revolutionized our understanding of the universe's timeline. By studying the decay of radioactive elements in stars, we can now estimate their ages with remarkable accuracy. This technique allows us to trace the evolution of galaxies like our Milky Way. By dating stars in different galactic regions, we can understand how galaxies formed and evolved over billions of years. Furthermore, nucleocosmochronology provides independent estimates of the universe's age, complementing other methods like studying the cosmic microwave background radiation. The consistency between these different approaches strengthens our confidence in the current estimate of the universe's age. This field also helps us understand the processes that occurred in the first few minutes after the Big Bang. By studying the abundance of light elements like lithium, beryllium, and boron, we can test and refine our models of the early universe.
If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating insights into space exploration and astrobiology, and be sure to let us know in the comments which planet you think is the most promising for future human habitation. Until next time, keep looking up, keep asking questions, and never stop exploring the wonders of the cosmos. The universe is waiting to be discovered.